Good morning, everyone. Myself, Mahesh Shirur, professor. So today I am going to explain you the model 4 of applied hydraulics, that is hydraulic machines. Okay, and that part first. Okay, impact of jet on the curved vents. Okay, here the curved vents will be there. So if the water is applied to it or jet of a water is forced to it, okay, then what is the effect? Okay, so first on definition or introduction, impact of jet is the force exerted by jet of water, okay, on a vane, that is plate or bullet, which comes in a path of jet. The force exerted by the jet on the vane can be obtained by using the impulse moment equation, which state that the impulse at a force exerted on a body is equal to the rate of change of momentum in the direction of the flow. Okay, that is the rate of change of momentum in the movement of the water, that is in the direction of the flow. That is a force, that is f of dt change in time is equal to m into change in velocity. Therefore f force is equal to m upon dt, that is change in velocity. Therefore force f is equal to mass of liquid flowing per second into change in velocity. Therefore force f is equal to mass of liquid flowing per second is equal to rho into q. Rho is the density, q the discharge, and change in velocity is from v1 to v2, that is v1 to v2. Okay, therefore force exerted by the jet on a stationary symmetrical curved vane striking at the center. Okay, this is one problem. Okay, so if this is the pipe and this is the nozzle, and this is the jet of the water flowing from that pipe or the nozzle. So this is symmetrical curve vane. Okay, okay, then if the water is striking or hitting the curved vane at the middle, then what will happen? So this is the line, center line of that, that is equal to 180 line. Okay, so this is the curved veins at top and bottom. Okay, so this center line, from the center of the curve, just I will draw an inclined line touching the two of toe or two of that the jet of the water that will be flowing, that is the curved vein. So from this dotted line, see here, it is touching at that curved line. After that it will be a straight line. Okay, so I will call this velocity v, which is hitting the vein and passing to it. Okay, as it is inclined, okay, we are going to resolve it into horizontal component and vertical component. Okay, so before that, so this is a fixed way, not it is not moving. Okay, see here, this is the, and it is fixed condition is here. So when we hit the, when the force of water is hitting to it, so it is, the vein is not going to move. Only the force of water that will be hitted, it will be passing through this veins of symmetrical veins. Okay, so coming to this velocity v, so that resolved into vertical is v sin theta, horizontal into v cos theta. So this portion is, okay, 180. So this angle is 180 minus theta, that is called as deflection angle. So this here also theta will be there. So after striking the vein, the jet of the vein tangentially with this same velocity v. Since the vein is smooth, this tangential velocity has two components as shown in the figure. So this forms a tangential velocity which is having two components, that is v sin theta and v cos theta. Okay, the force exerted by the jet on the vein. Okay, the direction of the jet can be obtained by using the impulse moment equation. Okay, the direction can be obtained by, before that I told you, moment equation, from that we can be obtained. Okay, so let d is the diameter of the jet and a is the area of the cross section of the jet, and v is the velocity of the jet. Okay, and theta is the angle with which the jet leaves the vane. Okay, we know that from the impulse moment equation, force F is equal to rho into q into v1 minus of v2. Hence F is equal to Fx, q equal to a into v, then v1 is equal to v and v2 is equal to minus v into cos theta. Therefore, now force in x direction, horizontal direction, is equal to rho into v in a into v into v minus of v into cos theta. Therefore, rho a into v is equal to v into 1 plus cos theta. Therefore, force in horizontal Fx is equal to rho into a into v into v square is equal to v square plus 1 plus cos theta. Okay. Similarly, force exerted by the jet of the vane in the direction perpendicular to the jet is also given by the impulse moment equation. Before it was in horizontal direction in okay 180 degree. Now it is perpendicular, that is 90 degree. Then what will happen? We know that a force from the force moment equation, F is equal to rho into Q into V1 minus of V2. Hence Q is equal to area into velocity. Here the force is equal to in terms of y direction, that is Fy. Previous case it was Fx, and V1 is equal to 0, initial velocity is 0, and V2 is equal to V into sine theta, that is vertical component. Therefore, Fy is equal to rho into V into minus of V into sine theta. Therefore, force in y direction is equal to Fy equal to minus rho into A into V square, V into V square into sine theta. Okay, one note here important: the angle of deflection of the jet is equal to 180 minus of theta, that is 180 degree minus of theta. If theta is equal to 0 and Fy is equal to 0, then Fx is equal to 2 into rho into V square. Then if theta is equal to 90, then Fy is equal to rho into A into V square and Fx is equal to rho into A into V square. If theta is equal to 180 degree, then Fx is equal to 0 and Fy is equal to 0, because no force will be exerted on that vane. Okay. Next one, force exerted by the jet on the moving symmetrical curved vane getting hit at the center. Okay, it is symmetrical curve, but it is here in the previous case it was fixed. In this case, it is symmetrical and smooth curved vanes, but in this case it is not fixed here. In this ends, it will be not fixed. When the force of the water is hitting this curved vane, sometimes the curved vane may be moving. That is, this is the initial velocity. After that, it will be v minus u. That is after change or moving of the vane. That is change in. So similarly, this can be resolved into vertical and horizontal components. So that is Fy and Fx. In the previous case, Fy into V into sin theta was there, and in the previous case, Fx is equal to V into sin V into cos theta was there. Now, as it is moving, Fy is equal to V minus U into sin theta will be there in the vertical component, and Fx is equal to V minus U into cos theta in the horizontal direction. Similarly, let D is the diameter of the jet and A is the area of cross section of the jet, and V is the velocity of the jet. Theta is the angle with which the jet leaves the vane, and U is the velocity of the moving vane, and V minus U is the relative velocity with which the jet strikes the vane. Considering the vane to be smooth, the jet of the water after striking the vane leaves it with the same relative velocity v minus u tangentially yeah, shown in the figure. Okay, and this is forms a tangential here as shown in the figure. Force exerted by the jet on the moving symmetrical curve in when in x direction or in direction of the jet can be obtained by using impulse moment equation, that is previous case F is equal to rho into Q into V1 minus of V2, where F is equal to Fx and Q is equal to A into V. V is nothing but initial minus final. Okay, final minus initial, and v1 is equal to v minus u final minus initial, and vt is equal to minus of final minus initial into cos theta, that is horizontal. Minus sign means opposite to the flow. Okay, therefore force in x direction fx is equal to a rho into a v minus u into v minus u minus of into minus of v minus into cos theta. Then simplifying, if you'll get force in x direction is equal to rho into a into v minus u the whole square into 1 plus cos theta. Okay, so next one, force exerted by the similarly force exerted by the jet on a moving symmetrical curve when in the y direction, before it was in x direction or in the direction perpendicular to the jet, is also given by impulse moment equation. Therefore F force in y direction is equal to rho into q into v1 minus v2. Here F is equal to Fy and Q is equal to V minus U, and initial velocity V1 equal to 0 and final velocity V2 is equal to V minus U into sin theta, vertical component. Okay, therefore Fy equal to rho into A into V minus U into 0 minus of V minus U into sin theta. Therefore Fy is equal to minus rho into A rho into A into V minus U the whole square into sin theta. Negative sign means opposite to the flow. Since the vane is in motion, okay, because when the force of the water is hitting that vane, the curved vane, it will be moving. So because of this wave in the motion, work done per second by jet in the direction of the jet is equal to any force in the direction of the jet into displacement upon time. Therefore, work done per second is equal to Fx into velocity of the vane, that is equal to Fx into u. Okay. Therefore, work done per second is equal to Fx in force, and that is equal to rho into A into V minus U the whole square into 1 plus cos theta into U, as in previous case. Therefore, we know that efficiency is equal to work done per second by the jet of the vane divided by kinetic energy of the jet and inlet. Therefore, kinetic energy is equal to half into mv square, that is equal to half into m is, that is m value, rho into q into v square. Okay, therefore kinetic energy is equal to half into rho into q is equal to a into v, that v square is nothing but v into v square is v cube. Therefore efficiency is given by neta is equal to rho into a into v minus u the whole square into 1 plus cos theta into u divided by half into rho into v cube. Therefore efficiency is equal to 2 into u into v minus u the whole square into 1 plus cos theta divided by v cube. We call that as equation number 1. Therefore, condition for maximum efficiency, when the maximum efficiency will be there on that jet of a vane, that is the to maximize the efficiency, the condition is that do u by do in dou by dou u in terms of efficiency eta is equal to 0. Okay, therefore dou u by, you have to differentiate dou u by dou u equal to 2 into u v minus u the whole square into 1 plus cos theta divided by v cube, that is equal to 0. So for the simplification, okay, practically 2 into 1 plus cos theta is equal to vq, that is not equal to 0. Hence dou u by dou v is equal to u into v minus u the whole square, that is equal to 0. Therefore dou u by dou u equal to v into v square plus u square minus 2 into u, that is equal to 0. Dou by dou u equal to v into u into v square plus u cube minus 2 into u square into v equal to 0. Note v square plus 3u minus 4 uv equal to 0. Then we have to simplify, okay, into two components, that is equal to v square and minus 3 uv minus uv plus 3x square is equal to 0. So we get two values, v minus 3u and v minus u equal to 0. So practically v minus u does not equal to 0, therefore v minus 3u equal to 0, therefore v is equal to 3u. Okay, therefore the condition for maximum efficiency is that the velocity of jet should be 3 times the velocity of the vane. Important, the condition for maximum efficiency is that the velocity of jet should be 3 times the velocity of the vane. Hence using this condition in the equation number 1 as in previous, so therefore maximum efficiency is equal to 2 into u into 3x minus 3u minus u the whole square into 1 plus cos theta, that is 3 into u cube. So simplification will get condition for maximum efficiency is equal to n eta maximum is equal to 8 divided by 27 1 plus cos theta. Thank you.